In this video, we're going to be talking about binary and other bases. So for humans, in base 10, each digit can have a value of 0 through 9. Each digit is worth a power of 10. So this is something that you've likely seen before because we normally count in base 10. Let's consider a number like 3,725. So when I say each digit is worth a power of 10, it means that going from the rightmost spot to the leftmost, it has more value. So the first thing that you have, the thing is in the ones place, like 5 times 10 to the 0. And then next I have 2 times 10 to the 1. And then next I have 7 times 10 squared. And then finally I have 3 times 10 cubed. So we often talk about things like 5 being in the ones place, 2 being in the tens place, 7 being in the hundreds place, and 3 being in the thousands place. We have a sense of what this number means and how big it is. This kind of numbering system where it goes from, for us, right to left, from the least significant to the most significant digits is called a positional number system. Now, everything that we've done with decimal before, we can do with binary. Binary is base 2. So rather than having the digits 0 through 9, I have the digits 0 and 1, binary digits, aka bits. And the reason that we like to use binary rather than base 10 is because of the way computers are built. So computers are really good at storing on and off. Binary numbers are going to use this to store arbitrary values. We just have 2 digits, 0 is off, 1 is on, and the place value uses powers of 2 rather than powers of 10. So looking at this example, 101111, I know we read it from left to right, but going from least significant to most significant, I have a 1 times 2 to the 0, 1 times 2 to the 1, 1 times 2 squared, 0 times 2 cubed, 1 times 2 to the 4th, 0 times 2 to the 5th, and 1 times 2 to the 6th. And so again, this is a positional number system where the placement of that 1 and 0 tells you how much worth it has, how much it contributes. So let's think about how we could count in binary. If you just have 0, it's 0, and one thing you might notice here is that I have this subscript 10, which I sometimes use to show what base it is in. So 0 in base 2, which is in the table, is just 0, and I've just got some leading zeros there as well. And that's 0 in base 10. Now a 1 is also 1 in base 10. But a 2, I ran out of bits, so I need to make that 1 0. And then 3 is 1 1, 4 is 1 0 0, 5 is 1 0 1, 6 is 1 1 0, 7 is 1 1 1. And so the way that this works is if I need to go over another spot, because I can't get any higher than 7 now, is I need to put a 1 in the next spot over, flip all the 1s on the right, and then turn that first 0 into a 1. That's going to give me 8. And in this case, I just gave myself some leading zeros just so you can see how the flipping happens, but for now, all of the rest is going to stay the same, right? Because I only need these 4 bits to really represent 8. Now that we know what binary looks like, we can talk about converting between binary and decimal. By the way, this is just how unsigned values are stored. So unsigned here just means we're just going to talk about positive values for now, and we're not going to deal with any negatives, just for the time being. To see what a binary number is in base 10, you just add up all the values of all the 1 bits. So where I had that 1 times 2 to the 0, and then 1 times 2 to the 1, and then 1 times 2 squared, I just add all of those up. And if you do that going from, again, I'm just going from right to left, I'm going to have 1 plus 2 plus 4 plus 16 plus 64. And you'll notice here, like, I skipped the 8s place and the 32 place because they were zeros. Once I add all those up in this particular example, it just ends up being 87. So that is the basic idea of how you convert between binary and decimal, but we just have to know those powers of 2. Decimal to binary requires a little bit of division, maybe. So if you are given a number in base 10, How do we figure out its value in binary? We'll see two common ways to do this. So let's look at this via an example with 51. Now remember, each bit is going to contribute to a sum. One is going to contribute something like the digit or bit 1, and 0 is going to contribute nothing. If it is a 1, it's going to be some power of 2 depending on its position. So 51, for example, let's guess. Let's put a 1 in the 64's place. Okay, well, unfortunately that was not the right thing to do because 2 to the 6 is 64, which is bigger than 51. So I can't make this be a number larger than 51. So that goes away. What about if I put a 1 in the next spot over, which is the 32 spot? Well, in this case, 32 is less than 51. Since 32 is less than or equal to 51, it's fine, and that 2 to the 5th bit must be a 1. Now, 51, we've used up 32 of it, so that leaves us with 19. So now that we used up 32 of the 51, we are going to be left with 19, and the remaining bits have to add up to 19. So the next spot over we have is 16, and that doesn't exceed the 19, so we're good. So I can put a 1 in that 16 spot. That leaves me with 3. Now, if I put a 1 in the 2 to the 3rd spot, that would be 8, which is too big, so I got to stick a 0 in there. And similarly, 2 squared, which is 4, is bigger than 3, so I got to stick a 0 in there. That leaves me with 2 to the 1, or just 2, which is less than 3, so I can put a 1 in that position. And then finally, I'm left with 1. I'm just going to put a 1 there, and I've used up everything. I'm left with 0, and so now I have my number 51 in binary. This technique is called a reduction of powers. Basically what I did was figure out what the largest power of 2 was that I could use. So what you could do is you could just guess and go larger and larger powers of 2. If you're pretty good at your powers of 2, like you know where they are, you might be able to figure it out pretty quickly. But once you get to one that's too large, you know to stop there. You may be also working with a fixed number of bits where we tell you that the solution needs to be like 8 bits long or 16 bits long. That also is possible, where you would just know where to stop. Let's look at a different technique where we're going from the least significant bit to the most significant bit. Now, let's think about what it means for a number to be odd or even. If a number is odd, it's some even number plus 1, right? Otherwise, an even number is just 2 times some other number. Now, because of the way that least significant bit place works, that least significant bit, if that value is odd, it has to be 1. Every other bit is going to contribute some multiple of 2 to the sum. 51 is odd, so that least significant bit must be 1. Now, how do we figure out the rest of the bits? I'm going to divide by 2, and that leaves me with 25. The remainder, by the way, is the thing that went in that spot 1, right? Because it's 51 is 25 times 2 plus 1. So if I divide by 2, just divide, the remainder goes in that last spot, that's going to give me 25. And so what it effectively does is like just slide all the other bits over so that we can continue this kind of process. So that 1 gets discarded, and now what we're left with is kind of like the next thing going over from right to left is kind of like that 2 to the 0 bit now. So let's convert 25 to binary. 25 is odd, so that least significant bit must be 1. So 25 is 12 times 2 plus 1. So that's where I put that 1. And I'm going to divide by 2 to get my 12. So that effectively gets rid of that 1 and slides everything over. So 12 is even. So that gives me the next bit being 0. 12 divided by 2 is 6, so that gives me that next bit being 0. So 6 is even, and so like I said, that bit has to be 0, but now 6 divided by 2 is 3. So since 3 is odd, that next bit must be a 1. Divide 3 by 2, that's going to leave 1, because 1 times 2 plus 1. So that's going to leave us with 1. So that next bit must be a 1. And then finally I have a 1. And when you divide 1 by 2, it's going to leave a 0, so I can stick a 0 in there. And you could keep going because 0 divided by 2 is 0, and 0, the remainder is 0. But all of the remaining bits are just going to be 0. So I could just keep going, which maybe I have to do if I tell you to fill up a certain width, but here we're good. Like, I'm just going to leave it as is. Now that we kind of have a sense of what decimal and binary look like, we can actually do math. We can add. Adding unsigned, aka like we're just dealing with like positive numbers right now, is easy in binary. It's just 2-digit values. So 0 plus 0, 1 plus 0, 0 plus 1, 1 plus 1, and 0 plus 0. And we need to have carries. We're going to add bit by bit, starting from that lowest order bit. 0 plus 0 is 0. 1 plus 0 is 1. 0 plus 1 is 1. Okay, here's a weird one, right? 2. 1 plus 1, that's 2, but I don't have the digit 2 in binary. So I need to turn this into 1, 0. I'm going to put a 0 there, and I'm going to carry the 1. So 0 plus 0 is 0, plus that carry 1 is going to give me 1. And that's it. So this looks really similar to how we did addition with decimal, as you have probably done before. The only thing that we need to add are these four cases, and then we have to think about carries. So because we have to propagate the carries, we end up with 8 cases. 0 plus 0, 0 plus 1, 1 plus 0, which is just not going to have a carry anywhere, and then 1 plus 1, which is 0 with a carry of 1. And then in the bottom half of this table, I have the same numbers, only I had to carry a digit in from wherever I came before. So we're going to carry into the next column, or we need to carry from the previous column. Subtraction is similar. You can go right to left. The least significant bit is to the most significant. So 1 minus 0 is 1. 1 minus 1 is 0. Okay, 0 minus 1. That one is -1, but we don't have negative numbers. Luckily, it's a larger number, so we have to borrow. So we need to borrow from the next left-hand column. So that ends up being -1 there. And then now I can subtract, which is 1 minus 1. And now I have this -1 here, so I got to borrow again. 0 minus 1 minus the one that we borrowed. We'll have to borrow from the column to the left, and that's going to end up with me having 0. And then that final column is -1 and 1 because of the way that we borrowed, but luckily that's just 0. So that's going to leave me with 0, 0, 1, 0, 1, which in this case is 5 in base 10. And I'll note to you that we had to borrow twice. So similar to addition, we have these rules for binary subtraction. It's subtracting bits, working from least significant to most significant. You just need to propagate borrows into subsequent columns. Just like addition, there's 8 possible cases. So you can actually think about how to, if you just had one column, you know what to do, and then you can think about cases when you have 2 columns or more, and you'll see how it breaks down into those smaller cases. It is a little maybe tricky to like keep track of all these borrows, but we have done the same thing with decimal before in our lives when we're doing long subtraction. So it is the same concept. All right, so I'm gonna borrow from the next column, or I'm gonna borrow from the previous column. Those are my cases. Now, one reason not to use binary is because it takes a lot of space. I mean, you only have 2 digits, so it just gets a lot longer than that decimal number, right? So you can write down the number 999 with 3 decimal digits, but it's going to take way more digits than that to write it down in base 2, right? So another nice compact way of writing binary numbers is hexadecimal. Hexadecimal means base 16. Each digit here is going to represent 4 bits. So this is nice to convert between binary and hexadecimal because I'm going to take my number, I'm going to split it into groups of 4. So I have 1, 1, 0, 1, which is my first grouping, 0, 0, 1, 0, next grouping, and 1, 0, 1, 0, third grouping. And now I'll explain this in a second, but these all are particular symbols in hexadecimal. So binary is a 12-bit number, but it's only 3 digits in hexadecimal. Since hexadecimal has 16 possible digit values, I have the numbers 0 through 9, but I need to do something for 10 through 15. So it ends up that it's going to be 1 for each possible pattern of 4 bits. So 0, 0, 0, 0 is 0. And then once I hit, when I go from 0 to 9, those are the numbers we're used to. But 10 is going to become A, B is 11, C is 12, and then going up at the top is F is 15. These all correspond to binary numbers as well. And it is good to memorize this particular table. So looking again at another binary number, it's 10 bits. I'm going to break it up into groups of 4. I need to add some leading zeros to the binary number. And then I can take each of those and convert it. So 0, 0, 1, 1, I know 1, 1 is 3. 0, 1, 0, 1 is 5. And 1, 1, 1, 1 is F, right? Because F is 15 in decimal, but it's F in hexadecimal and 1, 1, 1, 1 in binary. Just like base 10 and base 2, hexadecimal is a positional numbering system. It uses base 16. Each digit is worth 16 times the digit to the right. So let's look again at this kind of way of breaking up the numbers value. Let's look at 5BE9. 9 in that rightmost spot is 9 times 16 to the 0. Then I have E, which is 14, so it's 14 times 16 to the 1. B, which is 11 times 16 squared. And 5, which is 5 times 16 cubed. And I can add all this up if I wanted to see what it was worth in decimal. So converting is just to add up all those values. And this ends up being 23,529. And this one is also a nice example in saying that it took 5 digits in base 10, only 4 in hexadecimal. It's more compact. One way to convert decimal to hexadecimal is a very similar technique like we use for decimal to binary. Basically what's going to happen is you're going to grab that remainder, which I'm using the percent sign here, to get the remainder of that digit with 16, and then I'm going to divide by 16 and just take what's left over and continue that process. Right? So that is how you would convert from decimal to hexadecimal. Now that we kind of have a sense of what decimal, hexadecimal, and binary looks like, we can do arithmetic with numbers in hexadecimal. There's a couple of ways to do it. I have convert to binary, maybe thinking about it through base 10, and then performing arithmetic directly in base 16. If you want to convert to binary, so we already know that a single digit is going to be 4 bits in binary. So A is 1010, and 3 is 0011. So I can write it out that way. I can do the same thing with B9, and then we already know how to add in binary because I know, like, if I have 0 plus 1 and 1 plus 0, that's 1 and 1. 0 and 0 is 0. And then I might need to carry like I do here. But eventually I will get this number, and now I can break it up again into groups of 4, and that's going to give me F3. Another way to do it is to think about what the base 10 value is. This basically just relies on the fact that we have memorized our base 10. So a plus 9, we know a is 10, right? So convert it to decimal. And 10 plus 9 is 19. 19 is going to be 3 carry a 1. And now I have 1 plus 3 plus b, which is 1 plus 3 plus 11, which is 15, and then convert it back into hexadecimal. That's going to be F. Finally, you could perform the arithmetic directly in base 16. So if you wanted to, like, basically memorize the single digit sums, you can do so. I mean, you basically know how to do this in base 10 anyway, because you know that if I remove, like, if I carry from a 9, I get an 8, and 8 goes down to 7. You have a good sense of that. So here, if we do a plus 9, you just know that it's going to be 3, and it's going to carry a 1 into the next column. 3 plus b plus a carry is just going to equal F. So this one's the most direct method. It's just that we don't likely have an intuition for what hexadecimal looks like. Whereas with the second one, base 10, we do have a good intuition. If you do want to gain that intuition, it's useful to just start thinking about the table and at least memorize all of these, and then think about what happens when you do a carry into the next column. I guess one thing to point out here is that the thing that you carry always, as long as you're only adding 2 numbers together, is always just going to be a 1. Right? And then you can also get a carry in from the right. The last base I'm going to talk about is octal. Octal is another way to write binary. So remember, hexadecimal is 16, and 16 is 2 to the 4. So that's why you use four bits, and then it would turn into a single digit in hexadecimal. Octal is 8. 8 is 2 to the 3rd. So you can take 3 bits and then turn that into an octal digit. It is less compact than hexadecimal, but you don't need to use any letters. So if you memorize this, you'll see octal is base 8, which means we have the numbers 0 through 7. When we're in base 10, we have the numbers 0 through 9. And when we're in base 2, we have the numbers 0 and 1. So it always goes down 1. So let's take a look at an example of an octal. I'm going to take this number 110, 100, 101, and 010, and then 110 is 6, 100 is 4, 101 is 5, and 010 is 2. Octal is base 8. As I mentioned, it's got 8 possible digit values, which are 0 through 7. Each digit is worth 8 times the digit to its right. Let's look at an example of 5,174, which is in base 8. That 4 is 4 times 8 to the 0. The 7 is 7 times 8 to the 1. The 1 is 1 times 8 squared. And the 5 is 5 times 8 cubed. Once you write that out, you can add that up if you are interested, and you can figure out what the decimal value is, which in this case is 2,684. So just to summarize, we talked about these different bases. Base 2, which is binary, base 10, which is decimal, base 16, which is hexadecimal, base 8, which is octal. We'll talk about conversions between, or we did talk about conversions between all of these, and we showed how to add and subtract. Adding and subtracting looks very similar to what we did in base 10, but we need to develop an intuition for what those numbers actually mean and get a sense of the sizes. So that is it. Thank you for watching.